Good morning, everybody. In the last class, we discussed the RBF networks, radial basis function networks. So before that, we discussed the perceptrons. So with perceptrons, we started with two-layer networks. There was nonlinearity, and we were hoping that they would do better than the linear and discriminant function-based classifiers. But it turned out that perceptrons had exactly the same capability as the linear discriminant function-based classifiers. So it was a slightly disappointing. Then we kind of took a short detour and looked at the RBF networks. In RBF networks, there's an input layer, there's a hidden layer, and there's an output layer. And the hidden layer was nonlinear, and that had very good approximation capabilities. There's also a theorem, the Covert's theorem, which says that given certain conditions on the input data, you can always learn the input data with perfect accuracy. So now let us get back to the continuation of the perceptron topic. So with the perceptron, we found that it can only classify linearly separable classes, right? And also Minsky and Papert have kind of criticized that it may not be able to. So it obviously doesn't classify linearly non-separable data. Not only that, they kind of made a value judgment saying that it's not worth studying its multilayer counterpart, which was totally wrong. But anyway, that was just the judgment, and because of that, there was a kind of slowdown in research for almost a decade. So in the 80s, things have picked up again, and people started studying the multilayer perceptrons. And so suddenly they found that the MLPs don't have the problems that perceptrons had. Suddenly they become all powerful. So let us see how it works out. So in MLP, you have three layers, right? So you have three layers: the input layer, the hidden layers, just like in the RBF network, and the output layer. Okay, and it turns out that there are certain mathematical results which assure that if you have a hidden layer, just one hidden layer, and sufficiently large hidden layer, so that's the condition, right? You can pretty much solve any linearly non-separable class. So I'll make that statement more precise, more mathematically rigorous later. So MLP can approximate any continuous function, a multivariate function, to any degree of accuracy, provided that there are sufficiently many hidden neurons, right? And let us see what that means. So like I was saying, let's take an MLP, and without loss of generality, I'll take an MLP which has only a single neuron, okay, and a hidden layer and input layer. And there are weights going from input to the hidden layer. And from hidden layer, there is just weight projecting to the single output neuron. Because you can always, if you have multiple neurons, you can always think of them as multiple MLPs. So there's no loss of generality. So you have neurons here. Now we'll also assume that this neuron is a linear neuron. Let me explain what that means. I'll call these weights WI, second stage weights. I'll call these weights WJK, first stage weights. Okay, so now output Y and Y can be expressed as a sum of WI, the second stage weights, times Vj. So Vj is the output of any of these neurons. Then Vj itself is given as this is a nonlinear function, sum over these weights Wjk, first stage xk, minus this bias term, which takes the index Bj. So if you combine this whole thing into just one expression, it will be something like y equal to sigma. The summation is over I, the summation is over j, and so I Wi s of g sigma Wjk of f j here xk minus bj. Now the summation j goes from 1 to, let me call this m. So where m is the number of hidden neurons. Okay, so it turns out that if D is my desired output, So what happens is when you, so if you remember how we did the, define the classification in case of linear discriminant functions. So if it is class 1, we define some d equal to +1, and class 2 we define d as -1. So generally, so that's for classification. But if you are using it for approximation, then you try to if this is y, you try to make sure that y equals some desired output d. So you try to minimize the output error function, which is given as, right, and d minus y whole square. Sum over all the patterns, p equal to 1 to capital. Okay, so you try to minimize this. Now, in this process, so if I want more accuracy, that is less error, right, I just need sufficiently large. Okay, so more accuracy, which means smaller error, right, which means higher M. So the more hidden neurons I have, the higher the accuracy that I will get. And so you can basically, there is a theorem, this theorem by Sibenko, right, and other theorems also assures that if you want any arbitrary accuracy like 0.00000 something, right, then there exists a certain M, that is a certain number of hidden neurons, which will give you the desired accuracy. So it's basically, there's no limit to what you can achieve practically. So this can be achieved for, so it can approximate any continuous function over a finite domain. So it doesn't assure you approximation over infinite functions, from functions which so they have to continuous, so they cannot blow up, go to infinity anywhere, right? And they should be defined over a finite domain. If so, this is the target function. If these are the features of target function, and this is pretty reasonable because most real-world functions have this property. And continuity is kind of difficult, but anyway, it's a pretty natural feature. So most real-world functions have this property. Finite domain, obviously, that is true because any practical function will be of interest only on a finite domain. So if you have a target function like this, and if you have enough number of hidden neurons, you can always approximate it. So I also said earlier that if you have these functions which have the general form wi phi I of x, or you can also write it as sigma wi phi x ci. So phi is a general function, right? And it depends on x. X is an Rn, and ci is a bunch of parameters, which is in, let us say, Rm. So this is a family of functions because the same function parameters by a bunch of parameters. So it's a whole set of functions, some kind of a common form. And I'm trying to approximate an unknown function as a linear sum of such functions. All right, and we gave the example of Taylor series and Fourier series, a special case of this kind of a general expression. And just like in Taylor series and Fourier series, if you have, as you add more and more terms in the series, you get better and better accuracy, right? So here the summation goes from 1 to m. So you can see the analogy between this expression and this expression. So in this, so this is over k. K goes from 1 to more than. So yeah, this one goes over the m, the hidden neurons. Okay, so if you look at this expression, you can, so if I can write this as, the same expression I can write as, or I'll go to this page. The same previous expression I can write as I goes from 1 to m, and g of, I'll just simplify the whole expression, and this w first stage. So the g, okay, so the g is the function. This is the nonlinearity, and usually it's a sigmoid function. All right, I'm expressing the unknown function as a linear sum of the sigmoid functions. So the g is just like this phi. Okay, and so it comes under the general category of approximation theorems. and it's similar to this Fourier series and Taylor series. Now, what is this G function? This G nonlinearity in case of perceptron, we took it as the step function. Okay, but for an MLP, so this is for perceptron, but for an MLP, right, G, so the theorem requires that G should have the following properties. What are those properties? So first of all, it should be non-constant. So that seems like a weird thing because any function will have some variation. But anyway, just to make sure that, because in maths, when you make a theorem, you want to cover all bases, right, and then make it as rigorous as possible. So it's non-constant means it has to have some variation. You cannot give a flat line as a function. Okay, fine. So then the next property is monotone increasing. So it must be constantly increasing. Okay, it can never have, it can never decrease anywhere. So that is one. So then the third property is it must be continuous. Okay, and the fourth property is it must be bounded. Now, so only if the G has these properties, this approximation result is valid. That is, more accuracy means more greater M. So if, as you desire more and more accuracy, you just keep on increasing M, you will get that accuracy for some M. That's what theorem assures, and that assurance is valid only when G has these properties. Now, earlier we were using this step function for perceptron. Let us see if step function has any of these properties or all these properties again. It is non-constant, so that is fine. All right, monotone increasing. Actually, if you say monotone non-decreasing, it has, but it doesn't have monotone increasing. It is definitely not continuous, therefore it is out of the window. It is bounded, okay, which is fine. So step function violates the continuous, property. So it doesn't satisfy. So you cannot use a step function as a hidden neuron nonlinearity for an MLP. If you want to make use of the theorem, because that's what the MLP is good for. So obviously you want to make use of the theorem. So you cannot use the step function. Then what is a function which has all these properties? So let me erase this. The hell. Okay, so just a second, I'm trying to figure out. Finally. Now, what is a function which has all these properties? So let us look at two such functions. One is the logistic function, which is given as 1 by y equal to 1 by 1 plus e power minus lambda x. So lambda should be, basically it should be positive, but in practice we will also make it greater than 1. So this is one function. Now let us see if it has all the features. So this function looks like this. Right, it goes to +1 at plus infinity and 0 at minus infinity. It goes to 0.5 at 0. Right, and this function is non-constant. Obviously, it's monotonic. It is monotonic and increasing. It is continuous everywhere. It's bounded. It's not only continuous; it's also differentiable. But the theorem doesn't require that, so it is even more liberal than that. So this is one function which we can use, and we keep using this. Another function which we also use is the tanh function. The tanh function looks like this. Okay, it has again obviously has all these properties because the tanh is basically shifted and scaled version of logistic function. You can easily show that. So So we'll use these two functions in case of MLP, not the step function. So with this, you can easily show that MLP can solve the XOR problem, which was earlier not solvable by Perceptron. Let's see that. And here also, in case of MLP, you have 3 layers. Like I was just saying, you have input hidden in the output layers. Now let us see how you can solve the XOR problem. So in this case, just we will try to, just like in case of the perceptrons. So the earliest problems we have considered with perceptrons is AND gate and OR gate, right? And there initially we just showed how you can find the weights without even training, just by inspection. So similarly here we'll try to find the weights for an MLP so that it will approximate an XOR problem without training, just by straight inspection. So let us consider MLP which has one hidden layer and 2 hidden neurons in that hidden layer. It has 2 inputs x1, x2, and output is y. Now the 2 hidden neuron outputs are v1 and v2. So where they are given by v1 is g of x1 plus x2 minus 0.5. So here I'll assume that g is step function because I'm not trying to really solve any complicated approximation problem. It's a very simple problem, so step function should do. So I take this and v2 is g of x1 plus x2 minus 1.5. Y is equals g of v1 minus, so let us see what's happening here graphically. To take the first expression, g of x1 plus x2 minus 0.5, right, then the separator, the decision boundary will be here, because x1, because it is x1 plus x2 minus 0.5 is equal to 0, that is here. So for the second function, x1 plus x2 minus 0.5, that boundary will be here. So which means v1 function will be positive, it has y equal to 1 on this entire side and y equal to 0 on this entire side. Similarly for v2, on this side of the boundary it's all 1 and this side of the boundary it's all 0. Okay, so now if you take this function and calculate v1 minus v2, what will happen is there is a strip here somewhere like this, right? So this is this is x1 plus x2 minus 0.5. This is x1 plus x2 minus 1.5. There is a strip between these two. Within the strip, the difference is 1, and outside the strip, both sides, difference is 0. So v1 minus v2 will look like this. So now, so if you just pass it through a sigma to a step function, then the problem is the step function is undefined at 0, because it has a discontinuity. So to avoid that problem, you just subtract some small positive number from this expression v1 minus v2. So we'll subtract 0.5. And then what will happen is if you look at v1 minus v2 minus 0.5, that quantity will look like this. So v1 minus v2 minus 0.5, we'll have minus 0.5 here, plus 0.5 here, and minus 0.5 here. So step function of this, right? If you pass this whole thing to step function, you get 0 here, 1 here, and 0 here, and that's what we want for XOR function, right? In XOR, for here and here, you have 1, y equal to 1, y equal to 1, and here and here, that is 1, 1, and 0, 0, y equal to 0. So so by the simple construction, you could construct an MLP which can solve the XOR problem. So it's right away, it's just a proof of concept or a simple example, right, which shows that MLP can do something that Perceptron failed to do. So like I said before, that there are all these theorems which say that, which show that MLP is what is called a universal approximator, right? Can approximate practically any function. What is it? Any function? An MLP with a single hidden layer can approximate any continuous input-output function with arbitrary accuracy over a finite input domain, given enough number of nodes in the hidden layer. So that's what the theorem shows. So you can think of an MLP as an input-output function. That is, I have a network with input layer, output layer. I give input x and maps onto output y, right? And so just like in case of regression, you have an input and output, and you have some data, right? And you fit a line through this data. That is, the line should match input xi to some output yi. Okay, so similarly here, the MLP should match an input vector, right, x to an output vector y. Okay, input could be Rn, output could be some Rm. So it learn this mapping. This it's not even a multivariate function because it's a mapping which goes from n dimensions to m dimensions. So how do you train this network now? So you think of the network as again a black box. The approach is very similar to what we have done in case of Perceptron. Only thing is equations will become more complicated in case of MLP. So I have network here, input is x, output is y. And initially the network weights are all random. So when I give some input, it's likely to give a wrong output. So you compare that wrong output with the target output, the desired correct output. There you get some error and pass that error back to the neural network and change all the weights. So that is indicated by this arrow. The arrow says that the parameters of the box inside, right, are variable. So you vary the weights in such a way that next time around when you give the same input x, the y that you're going to get will be slightly closer to the target output p. So you see right here that this is a very different approach, right, to problem solving compared to the traditional approach, which is an algorithmic approach. So traditionally, if you want to solve a problem, by problem I mean a numerical problem, you have a bunch of numbers with which you start, and you apply a bunch of steps or procedures, right? And you crunch these numbers and get your final numbers. And you have to understand all the steps and you work out all the steps a priori, right? Whereas a neural network approach is totally different. You just have to have a lot of examples of that input and output data. After that, it will learn from experience, and very similar to how humans learn. Okay, so this training algorithm, which is called the backprop algorithm, which we'll describe in a minute, was discovered by many people. In the 70s, it was discovered by Paul Verbos. We did his PhD thesis at MIT on this, but nobody noticed that. It just went unnoticed, and that's because I think in the 60s there was this damaging criticism against MLP. So people thought it's bad to work on MLPs. So this thing went unnoticed. So then it was rediscovered by Rumelhart, McLaren, Williams in '86, and then around the same time, in '85, two other groups have discovered that the same algorithm, Parker and LeCun and so on. So the way it works is you can take actually the MLP is not just the training algorithm backdrop. It's not just for MLP, but for a single hidden layer MLP. It will work for any number of hidden layers. So let's take, for example, one hidden layer just for simplicity. I give an input X and the output of this goes to the next layer, then calculate output of the next layer. Then the output of this is then given to the next layer, and then output of the next layer is calculated, which is the output layer. So you get output Y. So these computations from the input layer to the output layer, that is called the forward pass. At the end of the forward pass, you get the output of the network. Now, once you get the output, you compare the output with the desired output or the target output T, and you get a variable called delta, which is like the error basically. Now, these deltas are now back propagated to the previous layers, and you compute some kind of an effective deltas at each of the hidden layers. You don't calculate deltas for the input layer, you only calculate up to the output from the output layer or to all the hidden layers. If you have only one hidden layer, then there's only one such computation. So once you have these deltas, so if you have a weight anywhere in this network, right, the update for that weight has this very simple and general form. So let us say the output delta at the output at this neuron, higher end neuron, is delta J, and the state of the neuron at the lower end is Vj. So this is delta I, this is Vj. The weight itself is Wij. Once these are computed, so Vj's are computed in the forward pass because the neurons outputs are all computed in the forward pass. So VJs are computed here. In the reverse pass, right, which is in the reverse pass, you compute all the deltas, output layer, hidden layers, and all that. Once you have that, for any given weight, there's a neuron at the higher end, there's a neuron at the lower end. For the neuron at the higher end, you take the delta. For the neuron at the lower end, you take the state VJ, and just take the product of these two, delta I minus delta I times VJ, and your update in the weight is proportional to that product. And the proportionality factor is a factor called eta, which is typically a small positive number, right? And this eta is called the learning rate. Okay, so how do you derive this? You take the output error. This is the total error. EP is error for the peak pattern, right? And this is the total output error. And EP itself is defined as the error for, so if you have so if I take a network like this, okay, so this is XK is the output of the kth input neuron. VJ is the output of the jth hidden neuron, and YI is output of the ith output neuron. So so here I'm using D as a desired output. Output is ith output is YI. So EI is D minus YI, and DI minus YI. Okay, and so therefore EP for the peak pattern is sum of squares of all these errors. So now Y is equal to G of, so here the total input going into a given neuron, I call this HJ. Sorry, HI here. And total input going into these neurons, I call this HJ. And here again we call this HJ first layer, and then this is HI second layer. Okay, so YI is G of HI of S, that is second layer total input, where HI of S is given by Wij, so this is Wij second layer weights. These are Wjk first layer weights. Okay, so HI of S is sigma Wij S Vj minus theta I of S. Then Vj of S, Vj of Vjf is given by G of Hjf, where Hj is total input going to Vj, this neuron here, jth neuron here, and Hjf is given as the summation, right, over K. K is input index, Wjkf times xk minus theta is the notation for the bias term. So how do you find the weights? The weights are very simple. It's like because you're using standard gradient descent. Weight anywhere is simply equal to minus of eta times dou EP by dou W. So this is a general expression. So specifically, we are looking at actually two sets of weights. So, or if you want to treat the bias terms also separately, then there will be four sets of weights. Okay, so therefore, the update for Wjij S is minus eta times dou EP by dou Wij S, and so on. So for every weight parameter, that's a rule. So the same thing just takes on four different special cases. So you kind of do the derivative and calculate this, all this. I'll skip all the derivation. So the only thing you have to remember in this derivation is this meaning of this new variable called delta. So let me just explain that. So the output yi, and so this is the output of the hidden neuron Vj. This is xk. Delta at the output layer, I'll call this delta S, I is given by di minus yi times g prime. So now g is not a function, it is differentiable. Usually we use logistic function, so it has a derivative, right? Because when we use step function in case of the perceptron, when we encountered g prime, we had a problem because g prime is almost zero everywhere. So whereas you won't have this problem here because the derivative of the logistic function is not zero everywhere, and there's a derivative. So the input here is hi of s. So you have hi s. So these are the deltas available at the output, ith output neuron. At all output neurons, at ith output neuron, there is a delta. So now I said we have to calculate the deltas at the hidden neuron. So this is delta fj. So in addition at this neuron, in addition to vj, we should also calculate delta jf. Okay, how do you calculate that? So deltas at the hidden layer are calculated in terms of deltas at the output layer by some kind of a recursion. How do you do that? So delta j at the first stage, the hidden layer, is given as sigma uh, delta I of s wij. The summation goes over I. So what is happening here? You take the output deltas. This is my jth neuron. You feed them backwards. These deltas. So these are wij second stage weights. These are delta I at the output second stage. So you feed these deltas backwards, weighted by these weights, but used in the backward direction. You get some expression that you multiply by g prime, and here the total input into this neuron is hj of f, the first stage total input, hj of f. Okay, so you calculate deltas at one level, you backpropagate them, pass them through the weights, but weights are used in the backward direction. Sum them up, you get some quantity, right? That you multiply by this g prime value computed this neuron. So like that, you calculate the deltas correspond to the hidden layer, and you're done. Once you have this, right, your final update rule is simply this. You have deltas here, you have VJs here, and you have YIs here. So you have outputs of neurons at every level. You have deltas at all the neurons except the input layer. So we are done. If you have that, you are ready to update all the weights. How you update is, given the Wij, take delta at the upper end, take the Vj at the lower end, multiply them, and multiply by proportionality factor eta, and use that to update the weights. This is in principle, I mean, I didn't derive the whole algorithm, it takes some time, right? And so this algorithm, although we derived it, we explained the usage in case of a single hidden layer, MLP, but the same recursive rule applies to any number of hidden layers. Actually, it applies to even larger class of networks called the feed-forward networks, but I won't go into all that now. So it was a beautiful step, really significant progress from the case of a perceptron, which had only 2 layers and also very limited in its capabilities. Right, and also it's a very general algorithm because it will work for a wide class of feed-forward architectures. So the way you use the network is first you train it, that is you randomly initialize the weights and train the network using this backprop learning rule. And you stop the training when the error is sufficiently low, because the goal of training is to make sure the output error goes down. So obviously when error is sufficiently low, you stop training and freeze the weights. And then you start using the network by applying a new data set. So you use one data set for training, it's called a training data set. Another data set for testing, it's called the test data set or validation data set. So a lot of advantages to this kind of a network. First of all, it's a general solution to a large class of problems. And we'll see some examples of where you can use MLP in biology. I mean, it's a huge field, but I'll just show a few examples. And with sufficient number of hidden neurons, it can approximate arbitrary target functions. Right? We have seen that approximation video. It also applies to arbitrary number of layers and partial connectivity and so on and so forth. The only condition is it should not have any loops. Okay, so it works for what is called a feed-forward architecture. Maybe let me explain that. So we want to define a more general feed-forward network. It might look something like is one layer, another layer, another layer. So this can get input here. This is one input layer. This goes here. This goes here. There's another input given at this hidden layer. This goes here. This goes here. This goes like this. And this layer gets another input from outside here, and all these feed here, right? And then there might be two output layers, and you can imagine all sorts of architectures. So you can imagine any architecture. The only condition is there should never be any loop, because in this case, this is not a loop, because when I go from here to here, here to here, I cannot come back in this direction because all the weights are directional, right? So weights have a point in a given direction, so you cannot go back like this. So you can define any architecture with any number of hidden layers, any number of output layers, any number of input layers. The only condition is there should never be any loops in the network. Such networks are called feed-forward networks. The backprop algorithm works for that whole very large class of architectures. So it's very powerful. So training is local both in space and time. What I didn't tell me, I have time to elaborate all this because I need to really go deep into the derivation to explain this really. But basically what is happening here is, if you want to, so there are two kinds of computations that occur in this network. One is in the forward pass, other is in the reverse pass. So this is forward, this is reverse pass. During the forward pass, you calculate all the network neuron outputs, the VJs. In the reverse pass, you calculate all the deltas. So both these computations, so suppose I'm calculating the output of a neuron. To calculate that, I need only this information. All the neurons to which it is connected, and the end connection strengths, the weights. This is all that you need. And this neuron is physically connected to all these neurons. Therefore, it can combine them and calculate the output. So the computation of the output of a neuron is local in space, right, and in time, because I just need the previous input at the same instant. So similarly, if I want to calculate the deltas, I need deltas at this level, delta I, right, and using that, I calculate deltas in the next level. These are delta J's, first stage, second stage. Okay, so this neuron is physically connected to all these neurons, they're actual physical weights, right? And so it just needs information available locally to compute this. So this property of an MLP is important because, first of all, if you look at it as a physical model of the real brain, because ultimately these networks are inspired by the real brain. So if you think of it as a physical model of the real brain, then so this is how neurons would be communicating. Each neuron sends information to its neighboring neuron, to which it's connected, and so on. So that is one thing. Second thing is, if you're going to implement, so normally when you use these networks, you simulate them on a computer, you write a program and simulate them. This is a traditional computer. But suppose you map this on a parallel computer, where every neuron is mapped onto a real processor. Okay, so they should be really small processors, not like the cores that you use in your GPU machines right now. Really tiny processors, just like neurons, where a single processor can implement only a single neuron, so it takes a bunch of numbers from other processors, does a linear sum of them, passes it through a nonlinear function, and send the output to a bunch of other processors. Suppose you're going to implement like that. This algorithm is just right for that kind of implementation, because the way the computations and communications are described among various variables in the mathematical formulation is such that it shows the underlying parallelism, right, of the entire computation. So it's this kind of formulation of backprop makes it straightforward to map the algorithm onto a parallel machine, onto a parallel implementation. So next thing, the hidden neurons act as feature detectors. So we'll say more about this when we talk about applications of NLPs. So for example, when you train the network on, because when you train the network on some data, the meaning of the input layer is clear, right? Because you actually give some data from the real world and the input layer meaning is clear. Output layer meaning is also clear because if you are classifying something, then output layer or neuron states represent those classes. The meaning is clear. But what is the meaning of the hidden layers? Because we never said anything about the meaning of hidden layers. So it turns out that when the network is trained on some data, the hidden neurons also evolve at interesting response properties. So for example, there's one study where they trained a neural network to read text aloud. That is, the text input is given to the network and it's supposed to produce speech in the output. So it was trained like that. This was just an MLP. It's a very old study. In the hidden layer, the neurons have learned to distinguish between vowels and consonants. Now, the network was never told that speech, the basic units of speech, the phonemes, right, come in two categories, vowels and consonants. But the network automatically developed that kind of a discrimination, right? So the hidden layers, their hidden neurons, can therefore act like feature detectors. They can learn something interesting, although they are not told to do that. So in that sense, the solution developed by an MLP, you can think of it as a creative solution because it does things that it was not told to do. It does things on its own, in some sense, creatively. So these kinds of models are good when there is no model available, because when there's no physics-based model available, we don't know the underlying equation, underlying physics, and all that. This is just a curve-fitting model, so you can build a model very easily. So problems with MLP or backprop is that people complain that it's like a black box. You don't know what is going on. You just give input and get output. It's like garbage in, garbage out. All these complaints are there. To some extent, they are valid. So therefore, to kind of answer this complaint, in the early days of neural networks, people used to actually, right, after training the network, they would actually go into the network and see what the hidden layers are doing, what are they responding to, what is the meaning of the response of the hidden layers, and so on. But with the advent of deep networks, when you have 150 hidden layers, nobody has the time or patience to go into the network and actually see what the hidden layers are responding to. So the black box complaint, now people don't even care, right? Because brain is a black box, so it's okay if a deep network is a black box. Now, limits of generalization not clear. That is a real complaint. So I'll talk about that later on when we talk more about this problem of generalization. And also hard to incorporate the prior knowledge into the network. I'll also talk about that, elaborate that later. Training is a bit slow because there is no simple way to initialize the network using good initialization. You can only randomly initialize the weights. Therefore, to start with a network like that and find an optimal solution, it takes a lot of time, and also it's a gradient descent kind of a iterative algorithm, so it takes time to learn. It also has problem of local minima. Okay, so I think let us maybe okay. So when you develop a new network application, you first have to do a feasibility study. You first have to assure yourself that the problem warrants the use of a neural network. So sometimes, right, the problem could be as simple as if I'm trying to map some input X onto an output Y. Maybe just fitting it using a matrix, right, is good enough. Maybe the relationship between X and Y is so simple that I can represent it as by a matrix, right? And if that is the case, why do you need a neural network? The data is very simple. So you need to first make sure that it warrants a use of a neural network because the relationship between input and output is very complicated. So that is one thing. Second thing is, are X and Y even related? Right? We need to make sure that they're really related. Because suppose you're trying to predict, like, maybe Infosys stocks with the help of sunspot activity or something like that. You can always put garbage and you get garbage out. But that's what you will get, because the relationship between Infosys and sunspot activity is as observed. So even if you just train a network on such data and you get something, but it doesn't make any sense. So you need to make sure that the problem formulation is meaningful, it's feasible, right? And then you have to collect data, create a large corpus of training data. Then you train the network, then you test the network, and finally you deploy. So these are the stages of how we develop a network, right? So we'll discuss these stages, in more detail in the next couple of classes, and then we'll also look at some applications of MLP for the problems in biology. Okay, so let us take a break there, and we'll continue tomorrow.